I'm Maria Gotte-Johnson from MIT, and this poster is about using millimeter-sized CD foils for high-precision DT neutron spectrum measurements in direct drive inertial confinement fusion at the omega laser. In this configuration, we use a 1 millimeter diameter CD foil, 5 millimeters from the ICF target, and neutrons are generated by the imploding target. A fraction of them scatter elastically in the CD foil to give recoiled deuterons. And these deuterons are then momentum separated in a magnet to reconstruct an energy spectrum. This is what the foils we have tested in this study look like. Lots of collaborators from MIT, LLE, General Atomics, and Sandia National Labs. In summary, performance of a millimeter-sized CD foil, 5 millimeters from TCC, has been tested in omega direct drive ICF implosions using the MRS neutron spectrometer. We find that the foils survive and produce data that compares reasonably well with NPAF neutron spectrum measurements, but the inferred yield is low by about 20%, and the inferred ion temperature is high by about 5 keV. And to make this configuration useful for precision experiments, improvements are required, including in how the foil is mounted, in terms of characterization of foil oxygen uptake and density, as well as we need to do an investigation of blast impact on the foil prior to detection. I'll detail these in the poster. Motivation for this work: millimeter-sized CD foils close to the implosion have been proposed as a game changer for improving energy resolution and allowing time resolution in neutron spectrum measurements. There are several references down here that detail this, but the system has been proposed for time-resolved measurements of the neutron spectrum in the so-called MRST spectrometer, which is expected to give time resolution of 20 picoseconds and energy resolution of 100 keV. And it's also been proposed for improved energy resolution and primary peak precision measurements with the current MRS at NIF and at Omega. For this system, we expect a factor 2 improvement in energy resolution and a factor 4 reduction in ion temperature uncertainty, which really would be a game changer. The reason why this works is the resolution for this type of system can be expressed as a combination of resolution due to stopping in the foil, resolution due to scattering kinematics, and resolution due to the ion optics of the magnet. And this magnet broadening can be significantly improved with smaller, closer foils without impact on efficiency, which is very cool. The concept of using millimeter-sized CD conversion foils close to TCC for direct drive ICF was tested using the MRS on Omega on a series of December 4, 2018 implosions. The foils used are made using glow discharge polymer coating technique. And again, this is what they look like from the front and from the side. In these experiments, we use explode and pusher glass shell targets to generate the neutrons. Foil is 5 millimeters from TCC again, and then we have a magnet outside of the target chamber wall, which is used to momentum separate the deuterons, so they end up in a different physical location on the detector array, depending on their energy, so that we can reconstruct the energy spectrum. The foils, again, are nominally 1 millimeter diameter, 40 microns thick, and they're deposited onto a 40 micron tantalum backer. We used them on 3 different experiments on this shot day, and the results that we got will be compared to MRS operated with a hot press 4 centimeters squared, 57 micron thick CD2 foil, 10 centimeters from the implosion. The measured recoil deuteron spectra do clearly demonstrate that the foil survives through neutron production. This is the raw data here on the left-hand side from Omega shot 91960 fielded with this configuration. There are 2 parts to this spectrum. There is this knock-on deuteron component with knock-on deuterons directly from the implosion, from the deuterium in the fuel, which have been ranged through the foil assembly, through the 40 microns of tantalum and the 40 microns of CD. If we added more tantalum, this would go further down in energy, but this is what we have with the current thicknesses. This is the measurement that we're really looking for. This is the DT neutron peak, which is deuterons from the CD foil. And if we zoom in on that, the red curve here is our best fit to that peak using the simulated response function. we infer an ion temperature of 13.7 keV and a yield of 6 times 10 to the 13. This knock-on deuterons directly from the implosion part is actually pretty cool. It's an interesting side benefit in this measurement scenario because they can be used to determine the fuel ROR. In this particular example, we infer a fuel ROR of 2.5 milligrams per centimeter squared. Using all available information about the foils in the setup, the yield is underpredicted and the apparent ion temperature is overpredicted in the millimeter-sized foil configuration. These two plots on this slide show MRS inferred ion temperature compared to NTOF on the left and MRS yield divided by NTOF on the right. And let's look at the leftmost, 3 points first. These are the points from the millimeter-sized foil configuration. And we note that MRS ion temperature is high compared to NTOF, and the MRS yield is low compared to NTOF in this foil configuration. In contrast, if you look at the remaining points, these are from experiments running MRS with a standard standalone type foil configuration. And in this scenario, we have a 4 centimeter squared CD2 foil 10 centimeters from TCC. We see really perfect agreement with NTOF, suggesting that the observed differences for the millimeter-sized foil do arise as a result of the foil configuration. The uncertainties for the millimeter-sized foil setup are impacted by a number of factors that do not impact the 4 centimeter squared standalone CD2 foil data. These are all the details that go into the yield uncertainty calculation. These are all the details for the ion temperature uncertainty calculation, but I want to highlight a few particular contributions. The foil density uncertainty is 5% for the glow discharge polymer coated foils, which directly impacts the yield uncertainty. There's also, as of yet to be quantified, foil motion uncertainty. For ion temperature, again, the foil density uncertainty is a significant contribution. We also have a significant contribution from that glue spot that's used to mount the foil, as well as the oxygen content in the foil. We'll look at these in detail later in the poster. And again, foil motion that has not yet been quantified will also impact the uncertainty. The foil mounting technique used on the test shots is not ideal. Ranging through the glue and stock will increase width and inflate ion temperature. If we look at this picture again, we see that about 10% of the foil surface is obscured by this glue. So recoil deuterons that are born underneath this glue spot will range through the glue and stock and lose energy, thus broadening the peak. And our best estimate impact of this on inferred ion temperature is 0.8 keV, but the impact could be worse. And any worsening here will bring data into closer agreement with NTOF. And we got this 0.8 keV from a simple MCMP calculation of the MRS geometry that does not consider the magnet broadening, just the foil and the geometry. But we can compare no glue in black with a mock-up of the glue known composition in blue. We see that adding the glue gives this tail, which increases the effective broadening. And I want to note here that this can be readily improved in future experiments if we use a tab to attach the stock or even attach the stock to the back of the foil. This is not something that we have to live with. Another important factor is that there are significant uncertainties in the composition of the GDP-coated CD foils. And this includes a 5% CD density uncertainty and also impact of oxygen uptake over time. The density uncertainty is really directly on the number of deuterium atoms in freshly prepared CD. And this will directly impact the inferred yield since this calculation requires knowledge of the number of deuterium atoms. The manufacturer, GA, also tells us that CD picks up oxygen over time without losing deuterium content. And studies suggest a plateau over time in this oxygen uptake of around 6% atomic. But there's a question of how fast we get there and also what the actual number of this plateau is. So there's significant uncertainty in the oxygen content. And this will impact foil density, hence deuterium stopping in the foil, which impacts resolution and ion temperature inference. Run MCMP simulation of this as well, and MCMP suggests that not considering the oxygen will significantly inflate inferred ion temperature of order keV. Here, the black is with no oxygen, red is with 6 atomic percent oxygen. You can see a significant difference in the broadening. Again, this simulation is not considering magnet broadening, only foil and geometry. And I want to note here that the old standalone hot press foils, which are filled with further from TCC, are much more stable. They're not subject to these significant composition uncertainties. The other cool thing about filling the foil so close to TCC is that it's close enough to be picked up by the Omega target viewing system, which means we really can know the standoff distance prior to shot to very high precision, better than plus minus 100 microns. This is just my rough first cut at fitting this image. But the inferred yield suggests that it's not that well known. This is look at inferred yield impact as a function of standoff distance. Our nominal standoff distance is 5 millimeters, where we would infer 100% of the yield. If we infer 80% of the yield, which we did for these measurements, our standoff would then actually be 5.55 millimeters, which is significantly more. And this inferred yield suggests that the foil material is further removed from the implosions by the time that the neutrons reach it. Side note here as well is that direction of flow could actually significantly impact inferred yield in this configuration. We have seen directional flow in Omega of order 150 kilometers per second before, which means in the nanosecond before bank time, the tray could have moved 150 microns, and that would then have about a 7% impact on our inferred yield. So that could be a significant factor as well. But anyway, so what's going on here? We know that prior to shot, this alignment's really good, but the yield suggests that it's not. A Vistad calculation of unconverted laser light confirms that laser light ablation of foil material is not the problem. However, X-ray load impact is still under investigation. This plot is a Vistad calculation of worst case infrared unscattered laser light intensity on the CD foil surface. If I plug those numbers into the mass ablation rate formula from Mazzini, I estimate that less than 1% of the foil mass will be ablated due to unconverted laser light. And actually, probably substantially less, because I made all the worst case assumptions in this calculation. So this is not the explanation. But we note that foil moment prior to burn could self-consistently explain our observations. A further out foil will reduce efficiency, leading to reduced inferred yield. And a tilted foil would increase measured broadening, leading to inflated ion temperature. And this is why this X-ray load impact could be an important question. Brings me back to my summary. So again, we see that these foils survive. These are the very first tests with them, and improvements can clearly be made. We could use a thicker foil backer to avoid interference of these deuterons directly from the implosion, and improve stock attachment to avoid glue impact on the broadening. We can characterize the foils better, in particular in terms of oxygen uptake and density, which is required for lower error bars and higher precision data. And we also need to investigate the impact of blast on the foil prior to detection, because this could self-consistently explain our results. Thank you.